All right, good. Um, let's get started then. Good morning to all of you. Welcome in the 16th workshop on business process intelligence, which we would have liked to host in Sevilla, but we will run it online, obviously, given the whole COVID situation. So yeah, welcome everyone. Um, what I wanted to mention very shortly as an introduction, I'm one of the co-organizers, obviously. My name is Jochen de Weert. I'm from KU Leuven in Belgium. Together with Andrea Bouratin and Marwan Hassan, we have organized this workshop for the 16th time now. So it's always a very important workshop at BPM. This year, as you will see, we had a list of PC members. We would like to thank them a lot for their efforts in reviewing all the different papers that were submitted. It's always a quite intensive period, especially if given that many PC members are a PC member in different workshops of BPM. So thanks to you all for your reviewing efforts. That's much appreciated. And I also think it's much appreciated by all the authors that present today, and even by the people who got some more negative feedback in the end. What I wanted to mention, yeah, it was slightly disappointing this year, to be very honest with you. The success of BPI, we usually end up anywhere between 10 and 20, sometimes a bit more submissions to the workshop, but this year we only had 9. So that's rather disappointing. I think partly due to the whole like lockdown situation in Europe, obviously, and also the ICPM conference, where the deadline was now a bit earlier, and which made it that some people probably opted to submit it to ICPM instead of BPI. Anyway, we're still happy to receive 9 very good works. We conducted 27 reviews, or at least the PC members conducted those reviews, and ultimately we accepted 5 of those papers, which will be presented today. So here you see the schedule. We have decided to organize everything within one morning session. Given the fact there are only 5 papers, it's maybe a bit tight, but I hope we can still manage to get through the program on time and within only this morning session. So as you can see, we will start off with the paper by Mohamed Reza Fanisani, Mathilde Boltenhagen, and Wil van der Aalst on prototype selection. Then we have the paper by Gert Janssens, Willem-Benoit de Peyre, and Christel Vaas on enhancing discovered process models using Bayesian inference and MCMC. And then as a third paper that will be presented before a short break, it's Sebastiaan van Zelst and Yukun Kao with a generic framework for attribute-driven hierarchical trace clustering. And then after the break, and that session will be hosted by my colleague Andrea Bouratin, we have a paper by Hans Wijtjens and myself on process outcome prediction using CNNs and LSTMs. And then finally, we will end the workshop with Lisa Louise Mannel and Yannick Epstein and Wil van der Aalst, who will present their paper on the EST miner. All right, I think that's clear for everyone. In terms of maybe some arrangement given the online nature of this workshop, so the goal is for every author to present the paper within 15 to 20 minutes, at most 20 minutes. So I will be strict on that, so 20 minutes at most. And then we have roughly 10 minutes for questions and discussion. I would suggest that we only ask questions after the presenter finished his or her talk. This is a bit more convenient if we start to kind of intervene in the middle of the presentation. Now it's a bit more difficult, I guess, so I wouldn't do that. I would propose that if you want to ask a question, that you put a Q, just a symbol Q, the letter Q in the chat, and then I will give you the floor, and then you can unmute your sound and raise your question, okay? Is that clear? Any suggestions or questions? No? All right, that's it then. Then we can move to Mathilde, who will present the first paper. So Mathilde, the floor is yours.
Okay, so good morning. I share my screen. Can you see everything or?
Yes, perfect. At least for me, it looks good.
Good morning, everyone. So I'm Mathilde Bolton-Hagen, and I'm presenting the prototype selection using clustering and conformance metrics for process discovery. This work has been done with Mohammad Reza Panithani and Velvan Daras from the PAD team of Aachen University. And I'm Thomas Chatin and Joseph Carmona PhD student, and I work at LSV, Paris-Saclay University. So the context of this work, well, I cannot. Okay, the context of this work is process discovery, which is one of the main branch in process mining that aim at discovering process model from an event log. And the process model can be a BPNM, a Petri net, a workflow diagram, or other. And there exists a lot of different process discovery algorithms. Well, I don't know how to change the slide. Okay, sorry. So there are different discovery algorithms that work well on artificial data. But then when we go to real event log, the algorithm give very imprecise, complex, and particular process model. By imprecise, we mean that the event log are so complex, then we discover process models that are also very complex with many edges, many arcs and nodes. And so the process model contains more behaviors that really exist in the recorded event log. And also we call them those process model a spaghetti-like model because there are many arcs. So the model are complex also, so we cannot really read the model. So process model are usually used to for business teams who want to take decisions. And so it's good to have models that are human understandable. So this is the context of our work. And the outline of the presentation is the following. We will talk about the current method to reduce the complexity and the precision of process model. We will show the proposed method, the experiments, and the conclusion. So in order to get a simpler model and more precise model, we can reduce the event log that we use as input of process model discovery. And there are already some methods, which are pre-processing method on the event log to get a sample or a filtered event log. For instance, we can filter the event log in order to reduce the noise that we have in the event log. Or there is also a method that uses sampling only on the event log with some statistical metrics that says the sampling is good enough to represent the entire event log. And there is also a pre-processing method which uses instance selection. So for instance, it will take the process instances that are the most frequent in the event log. So we use only the sequences that are well representing the event log. From all those methods, we get one unique simple event log, which is used to process this as input of process discovery algorithm, and then we get a unique process model. But there are also other methods that use clustering to get different sublog, and then for each sublog we can get a process model, and then those process models are simpler and more precise to the given sublogs. But then having several process models is not very practical for business management business decision maker who want to analyze the entire process. In our method, we want to use clustering to get a sublog that represents the most the entire log. So our method is incremental, so we have 4 steps. And the first one is a clustering to get some prototypes. So how does it work? We have the entire log. We do a clustering method. In our case, the clustering method is a camedoid. And then we get different clusters, and we get the most representative trace of each cluster. With the data mining terms, we call them the centroids. Those centroids are what we call the selected prototypes. So we get the most representative trace of each cluster. And then we will use the selected prototypes as input of model discovery. The model discovery can be inductive miner, ALP, Smith miner. This is some choice that we made. We get a model, and then the third step is to evaluate the quality of this model. So for that, we compute fitness, precision, and give a balance of the two by using the F measure. At the first iteration of our work, we only keep the F measure. And notice that we compute the quality assessment with the entire log. So the process model has been discovered with the sublog, which is the prototypes, but then we compute the quality metrics with the entire log. If there are some traits that are deviating from this discovered process model, we iterate, and we will find representative of the deviating traces by doing another time a clustering. And then we will add the new selected instances to the prototypes and discover a new model and compare the F measure of the new model to the previous one. If the F measure is better, then it means that the process model, the new prototypes has been important in model discovery. The loop will stop at some point because by adding new prototypes, we will get a more complex model, and then the precision will also be worse, which will decrease the F measure. And so we stop when we get a model that is for which the loop is worse than the previous one. So we implemented the work in 2 tools, Prom and Rapid Prom, and there are some parameters. The first one is the number of clusters that we want to discover at each loop, and the second one is the algorithm to discover the process model. We use algorithms that return a sound process model in order to compute the different metrics. We did some evaluation with the BPI challenge event log, and we tried the different settings for the algorithm. So for instance, we tried 50 different thresholds for the inductive miner and 100 different thresholds for the split miner. And we compare our method to the one without any pre-processing. So when we use the entire event log as input of the model discovery, the statistical sampling, and the instance selection. The result for the fitness, precision, and F measure is given in this table. So we can see that in most cases, we have the best F measure. And this is due to the fact that our models are often more precise than the other. So we see that our method don't get a perfectly fitting process model. But this was, the aim of our work is to get more precise models. So we see that we indeed have more precise model, which is due to the fact that we find a sublog that represents well the different the different clusters that we can find in the event log. About complexity, we show two metric card also and the model size to show that our method give indeed a very simpler model. In most cases, our method gives a simpler model. So I think this is an improvement from the state of the art. So the conclusion of this work is the following. So we presented it's a pre-processing method which can be seen as a framework because we can change the algorithm to discover the process model, and also we can change the metrics that are used to compute to compare the different process model at each iteration. We assume that our method is slower than the other pre-processing method, but this is due to the fact that we use conformance checking metric in the process. But it's still, we don't use it so often. We use it once per loop, which is not too much. So the limitation of this work is that we don't really know how to set the number of clusters. So this is a parameter that one has to try. And I think it's also the same in data mining. Yes, and for future work, we think that we can do more work on doing other experimentation with other conformance metrics and also other algorithms. Thanks for your attention, and you can reach Mohammad Reza Fanifani on LinkedIn, Twitter, and by mail.
Thank you very much, Mathilde. That was a very nice presentation. So as I suggested, it would be great that if you want to raise a question to Mathilde or the co-authors who are also present, you put a Q in the chat, and I will give you the floor. So anyone who is willing to raise a question, please please do so. In the meantime, maybe I will start off with a question in that case. I don't see any Qs appearing. So it's a nice application of clustering. What I was wondering is, in your comparison, in your experimental results, you compare it with the statistical methods. Is that what you refer to? Is that like you select, for instance, the top K most frequent traces, for instance, as prototypes, or how should I understand that statistical method that you compare yourself to?
So yes, for the statistical method, we use the most frequent traces in the event log. So for instance, the top K, and we use those top K sublog as input of model discovery. Yeah, is it the question?
Okay. Yeah. And so, and you show that your technique currently improves upon, for instance, that baseline, let's say, right? So I consider that as a baseline. And as I read from the paper, you tested that with several settings, right?
Yes,
with several possible solutions that you select a top K % of most frequent traces, for instance, right?
Yeah.
Okay. I see that Will wants to raise a question.
Yeah, so thanks, Mathilde, for the nice presentation. If I look at this overview picture that we see here, then in step 3, you do a quality assessment, right?
Mm-hmm. Yeah.
While I was listening to the presentation, I like the quality assessment has two purposes. One purpose is to decide when you still want to improve the result.
Yes.
The other purpose is that you somehow want to talk about how good the method is, right?
How good the method is?
Like how good the model in the end is compared to the original log. I was triggered by your remark that, let's say, alignments make this method slow, right?
Yes, yes.
But in principle, you could do the quality assessment in the discovery approach using token-based replay,
yes,
right? You could then make the method much faster.
Yeah.
And only if you want to reason about the quality, you could use alignments. Because in practice, you just have a discovery technique. You don't need to compare it to other methods. Do you see what I mean?
I think so. Yeah.
So would that work, you think?
Excuse me?
Would that be a good idea to make it fast?
To incorporate the quality assessment, I mean, to use the quality assessment in the discovered algorithm.
No, I mean that you would use token-based replay while you are going through the iterations, because it's much faster. You use token-based replay rather than alignments. So you would get the discovered model very fast.
Mm-hmm.
Then only at the very end, you would measure the quality for comparing it to other methods using alignments. And so using only alignments to evaluate the final model, not to use alignments to evaluate the model through when you're going through the iteration with the increments.
Okay, I see. But I don't think that our method aims at giving the quality evaluation as outputs. So in my view, the quality assessment are mostly here to choose when we stop the loop.
Yeah.
Then, if I understand well, we could use the token replay only and not the alignment.
Yeah.
If I can add something.
Yeah, go ahead. We don't hear you. We don't hear you good, Mohamed Reza.
So in general, if we want to, if we use different techniques for somehow computing the compliance of the login model, so we can improve the performance. Absolutely. If, for example, we use the token-based replay, we can improve the performance. Also, for detecting deviated traces, we can use binary, somehow binary methods that say, okay, if it is aligned or not. So we could improve the performance definitely.
Yeah.
And just after returning the model, we could also enrich the model with some quality issues like conformance checking at the end. And yeah.
Yeah, I think the main thing of our work is the framework to show that we can use a discovery in this iteration and use some quality assessment, but we can change either the quality assessment and either the process model discovery algorithm. Mm-hmm. So what we want to show is really the framework and the experiments.
All right, thank you very much. I see Hans has a question as well.
Yes, thank you very much for your nice presentation, Mathilde. I was just wondering how sensitive are the results of your work to the number of clusters, like you mentioned yourself in your limitations, and also to the original seeding, because as I understood it, the model you're going to pick at random k traces, and then you start working from those. So what's the sensitivity to the number of clusters, and what's the sensitivity to this original random choice of traces?
So I think I will let Mohamed Reza to answer.
Thank you for your question. Actually, it's one of the limitations is we couldn't always guarantee to return the optimal result. So our result is really depend on the number of clusters. So, so we run the experiment and return the average value. We see that somehow a standard deviation is not far from each other, but as you said, it's somehow sensitive. We couldn't always return the best result. So the order of selection is important. Also, the number of clusters is important. And we couldn't always guarantee to return the optimal result. But it's not like that. For example, one time we have F measure 0.95 and sometimes 0.80. It is always, at least in our experiments, it's somehow 0.95 or 0.94, something like that.
Okay, excellent. Thank you.
Then Shiva, you can raise your question.
Hi, this is Sander from QT, husband of Shiva. Hi, thanks for your nice presentation. I had actually one maybe a bit detailed question. Like you mentioned, you get a centroid from each sublog. Could you elaborate a bit on how you get that, and yeah, what like how sensitive is the technique to that particular choice of centroid?
So in this paper, we use the caminoid methods. And so the caminoid method is like the Camin method, and it's based on a centroid, which is a kind of the mean of the vectors. So the most representative trace is a vector. I mean, it's a trace with a vector shape, and in the difference with the Camin method is that the centroid is from the input. So it's a trace that exists in the event log. So I don't know if it's clear enough. So it's a mean, but from the event log.
If I can also add something, so we consider each trace as a word, and we use the Levenshtein distance, edit distance of two words. So the medoid for the prototype that we select for each cluster is the trace that has the minimum distance compared to other with the other traces on that cluster. But
okay, so with Levenshtein, you take kind of the trace that has the least distance to all of the other traces in the cluster.
Mm.
Does that perform well? Is that a bottleneck, or?
Sorry, the bottleneck.
Is there any?
Go ahead, please.
In terms of runtime for your entire technique, is this a very limiting step, or is this is it done quickly?
Actually, it's very fast method. And for example, if I want to explain the complexity, it is n log n. So n is the number of traces in the log. So the process of clustering is n log n.
Okay, thank you.
Thank you very much, Sander. Then Mitchell.
Hi, good morning.
Good morning.
Thank you for your presentation. I really liked it. I've also spent a lot of time on the BPI'20 log, and I saw that you used it in your evaluation. And I found that the only way to really model this log in a readable way is to use label duplication. And I was wondering, maybe because you do clustering and you might see the same event in different locations in different clusters, and you're combining models in some way, does your model allow label duplication in the end, or is that just a no-no?
Mm.
So we don't use label duplication because we use inductive miner, split miner, and ILP miner. So we don't do any duplication in labeling. So in general, if one activity present in different part of traces, for example, inductive miner costs to having somehow loop back or something, some behaviors like that. But because the number of traces that we select before giving to inductive miner is very few compared to the original log, we don't have so many those behaviors. If I understand your question correctly. Please.
Yeah, so you don't combine models so much as you add more traces to your log and then generate a new model.
For example, in each step, we consider one event log. We add traces to prototypes, and again, we give the complete event log, the sampled event log to the inductive miner or different prototypes.
Yeah, so from one step to the next, the model may drastically change and put like a whole set of events in a very different place of the model because of a few traces that were added. Or is that not what I'm understanding?
Because as we see on the results, so we continue it. If we improve the quality of model, we continue adding traces. But in general, it could increase, for example, it could adding some new traces could decrease the quality of the model. And as you said, it could, for example, cause to have very imprecise process model, and we usually stop at that time and we don't consider those.
All right, yeah. Okay, thanks.
Maybe I can follow up with one extra question from my side. So currently, how did you implement the stopping condition in the algorithm? So how do you make sure that you get out of the loop? Do you really just look into the F measure score, and once it goes down, you stop, or what is the stopping condition right now?
The F measure. So if there is no improvement in F measure, yes.
Because that might be quite sensitive, right? You might see a small drop at a certain moment, but it doesn't guarantee that it wouldn't be better to continue and increase the number of prototypes. So that might be something that is of interest to investigate.
True. It could be happen to find the local optimum.
Yeah. Okay. Any other questions? If you want to raise them, it's final seconds to put a Q in the chat or raise your question directly. No? All right, Mathilde, Mohamed Reza, thank you very much for commenting on your paper and answering the questions. Then we can move on to the next contribution. And I think Gert will present his paper.
Yes, thank you, Jochen.
All right.
Just share the screen. You can see my screen now?
I can see it, yes.
Okay. Thank you everyone for being present today. My presentation will be about enhancing discovered process models using Bayesian inference and MCMC, Monte Carlo Markov chain. This is joint work I did with Benoit de Pere and Christel Vaas of Hasselt University. So the context is the same as the previous presentation. Actually, we have a process that generates event data and we discover a process model. But process models we discover using the current process discovery algorithms are typically like this, which means that they don't have any information about probabilities, typically about uncertainties. For instance, in this example model, we have request funding to go to BPI'20 assuming that it will be again in real life. Then our funding can be granted or rejected, and then we have to either cancel our plans or register, book the hotel, and so on. Can everyone see the process model?
No, well, I see your second slide right now.
Okay. So
we also are not in presentation mode according to what I see.
I'm sharing the wrong screen. Just I was starting. Now you see the process model?
Now we do, yes. Perfect.
Okay, I thought so. My apologies. So this discovered process model typically doesn't have any information about uncertainties or dependencies between probabilities. For example, it might be that when our funding is rejected, there is a higher probability, although not a complete 100% probability that our plans will have to be cancelled. While registering for the conference, booking a hotel, booking a train might be activities that in theory can be executed in any order. Some of the orders might be more probable, and depending on what happened before, you might start with one or other of the activities. So what we want to do is we want to learn probabilities given a model and given event data, and we will do that using Bayesian inference. I will start with a very simple example to show you how we can do it and what we can learn from it. Given this event log of 4 different traces with a specific frequency each, this event log actually leads to a very simple model that we can discover with two choice constructs, one choice between B and C and one choice between E and F. So for each of these choice constructs, we can define a probability. So we have a probability zeta1 that B is executed after A, and we have a probability 1 minus zeta1 that C is executed. And we do the same for the second one. Now the probability of seeing each of the 4 traces can be described by combining in a formula zeta1 and zeta2. So we see that if we call data 1 till 4 the probability of observing each of the traces, we can compute those probabilities using the zeta1s and zeta2s. And then we can say in our Bayesian model that the event log that we see, the data, is the result of a multinomial distribution with these 4 probabilities with a specific number of draws from it, a specific number of observations. And we also set our priors in Bayesian inference. We set both zeta1 and zeta2 to a beta distribution with shape parameters 2, which means that the prior that we set is uninformative. So it's most likely in our prior distribution that the probabilities are equal to 0.5. And then we give it the data. And this is actually the Bayesian model. This is the notation that's typically used for Bayesian models when you're using JAGs. So we give it the data, which is the trace frequencies and the number of cases that we saw. And then we can run this model to get to posterior distributions of all these parameters. So what we see now is that we have a posterior distribution of both zeta1 and zeta2. And we see that for zeta2, which is the orange distribution here, it is much higher than zeta1. So the second probability where we choose between E and F, it's much more likely that we go for E instead of F. While for the first choice construct, where we choose between B and C, it's a bit more towards 0.5, so it's more balanced, but still higher than 0.5. So we expect B to be more likely than C, but the difference is less big as for the second probability distribution. And we also get this information that gives us an idea about the actually the goodness of fit of our Bayesian model with the data. And I will come back to that later on. But we can do, because we can do more with it, suppose that our choice between E and F will depend on what happened before. Did we do B or did we do C? Just as in the example we just saw about the BPM conference registration and so on. So we can say that depending on whether you do B or C upfront, you will get a different distribution of probabilities in this case. So it will be zeta3 versus 1 minus zeta3 if we do C, and zeta2 versus 1 minus zeta2 if we do B. So our model is still the same, just that for 2 traces, the probability computation will be different, because it's, if we do C here, then we have another distribution, another probability there. We have one more prior that we have to set, and we can also add, let's say, additional variables that we want to compute. So we want to compute the difference between zeta2 and zeta3. This is just a trick so that we can analyze this difference more easily. If you again run this result, we see that we now also have delta and we have zeta2 and zeta3. And we see that zeta2 and zeta3, so the probability of executing E instead of F largely depends on what happened before. So if we first saw B, it's less probable that we execute E. If we saw C, it's much more probable that we execute E. So you can see here that there is a difference between the 2 situations of a probability of 0.63 and 0.86. And the delta is the difference between these 2 distributions. And we see here the confidence interval of this delta. And the value 0 is outside of this confidence interval. So we can reject the hypothesis that actually zeta2 and zeta3 are the same, which means that there is a difference, there is a dependency between those 2 choice constructs actually. But what we can also do is look at these informations I already pointed out, The DIC is the deviation information criteria, and it tells us how good the model fits with our data. And the lower this value is, the better our model fits. So we see that in the second configuration, the DIC is 19.01, which is lower than the first one. So our second model, where we had two different distributions for the second choice construct, fits better with our data. So it's a better description of the reality if we say that this choice construct, the choice between E and F, depends on the choice between B and C. And when I say this choice depends on this other choice, that's not a new concept. So we have long-term dependencies, but this is the different type of dependency because it's not a fixed. It's not if that happens, this will happen. It's if that happens, this will be more likely or less likely. But of course, there are many complexities in realistic models that make certain Bayesian models, let's say, not so straightforward to compute. For instance, if we have a parallel construct, it's not as easy to model using probabilities as a choice construct. If we have loops, our model can have an infinite amount of behavior, or can represent an infinite amount of behavior. So how can we model that? We might also have in our data unfitting traces, and we also want to model those. So to tackle these complexities, we came up with a generic algorithm that helps in building the Bayesian model, containing 9 steps. First, we split the event log into a fitting and a non-fitting part. For the fitting part, so the traces that can be replayed on the model, we construct a prefix automaton, and we add 2 types of escaping arcs. Escaping arcs based on transitions possible in the model that did not occur in the log, based on the work of Jorge Munoz-Gama. We call this the escaping end states. But also we add additional escaping arcs based on the activities in the non-fitting part of the log that were not allowed by the model, but we observed them, and we call these unfitting end states. And then for each state with more than one outgoing arc, we define a probability distribution because more than one thing can follow after this prefix. Then we can add constraints and additional variables like the delta we just saw, or we can add constraints to say that this choice construct should have the same probability as that choice construct, depending on what is the use case of what hypothesis do we want to test. And then for each normal end state, we can combine all the probabilities that lead to that end state to get a probability to end up there. And we can also define a probability to end up in an escaping end state, which means imprecision, or the probability to end up in an unfitting end state, which means let's say a less fitting model. So to give you an example, let's look at a more complex event log. This event log has 12 traces, some of which, if we compare them with this model, are non-fitting. In particular, the 2 ones that have only 5 activities don't fit with this model. So what we do is we create a prefix tree based on the fitting part of our event log. And we add the escaping arc. So the blue ones are activities that were not possible, but were seen in data. So these are unfitting, let's say unfitting transitions, unfitting end states. And the red ones are transitions that are possible in the model, but we didn't observe them. Then we look at all the prefixes with more than one outgoing arc, and we define the probabilities for those. And then we can add constraints. For instance, we see several times here a choice between F and H. We see it 4 times here for different prefixes. So if this relates to the hypothesis we want to test, we could say we want to add a constraint that these different choice constructs all have the same probability or have different probabilities. And then we can add variables to measure how different they are. We can then combine all the probabilities that we have defined to get the probabilities of each trace, which is each end state. And this will give us the following. So we have, for each fitting trace, we have how it is composed of, let's say, the probability construct, the choice constructs in the prefix tree. We have non-fitting traces, we have escaping arcs, which are imprecisions. We can have additional variables. Let's say we are interested in the difference between beta 4 and beta 3 here, and we have to define the priors. Here we have used beta distributions for probabilities with two binary probabilities, and we have used the Dirichlet for multinomial probability distributions. So what can we do with it? For instance, we can, as in the example, the small example before, we can see whether the funding rejected, if the funding is rejected, this has an impact on the cancellation of plans, or is it independent from each other, and how strong is that impact? If we have a parallel construct, are all of these, let's say all of these sequences, are they equally probable, or one or more sequences more probable? Is it more probable that we start with the registering, or is it more probable that we first book the hotel and then book the train, even though it can happen in all the different orders? What's also interesting, if we have a loop, which is not in this model, but if we have a loop, we can see the probability that we do an iteration of the loop. Is that constant over time, or does it decrease after 1 or 2 or 3 iterations, that it becomes less probable that you see an iteration? And finally, you can also test different models, alternative models. Let's say we change our model. We say that we first register for the conference, and then we book our hotel and our train in a parallel construct. Which of these models will have a better fit with our data? So it's similar to conformance checking, where you could compare both models to the data, and you have fitness and precision. But using this approach, you will have a statistically based goodness of fit measures to see whether it's statistically better one model over the other. So to recap, to summarize, we start from an event log. We go to a process model. So mostly I assume that the process model is discovered from the event log, but it can also be a hand-drawn process model, of course. But typically it will come from an event log, because we also need the event data to build a statistical model on top of it. And then we can use that statistical model to test hypotheses, to compare different process models, and so on. The algorithm is implemented in the R package proper for probabilistic process models that will help you with different functions to create the final Bayesian model and to run it in R, which is you have the process data and you have the process model, and then it will run you through the different steps to set the constraints, set the prior distributions, and so on, to find your Bayesian models and to visualize it, which is part of the BPI ecosystem for business process analysis in R. And the aim of this research is, it's still like ongoing research. The aim of it is to take process discovery to the next level. It's one of the current, let's say, approaches to add more more probabilistic foundations to process mining. There are other papers written at this moment that also try to use more probabilistic stochastic approaches in process discovery or conformance checking. This is one of them. There's still a lot of future work, of course, if you have large models, to make it feasible to let's say, to go through the algorithm to set all the different things without getting, let's say, overwhelmed by the complexity, because the prefix tree and the different splits can become overwhelming if you have a large data set, a large process model. And also the approach requires that you have a very good idea of which hypothesis do you want to test. If you don't have a very good idea of what you want to test, what is your end goal, it's very different to learn things from your Bayesian model output. So these are all points that will be the subject of future research. I thank you for listening, and I will be happy to answer every question that you have.
Thank you very much, Gert. That was also a very nice and clear presentation. So again, I would like to ask you if you have questions, put a Q into the chat and then I will give you the floor. So please go ahead. Yeah, I see Sander. Well, no, it was Sebastian, I guess, who was first. Sebastian, you can raise your question.
Yeah, thank you for your interesting presentation. You forgot to mention that we're giving an awesome tutorial on Wednesday, a little bit of marketing, but I'll do that in the next presentation again. My question is related to the data perspective.
Mm-hmm.
So to some degree, I think the Bayesian networks that you're learning show, let's say, unravel certain hidden dependencies and stuff like that. But I was thinking that in some cases, these rules that you learn, or that you can derive from from the Bayesian network, might be actually the result of some unknown underlying causalities that are partially data driven.
Mm-hmm.
So I was actually wondering that whether you considered a way to somehow integrate the data perspective within your framework.
We have not yet considered it, but it should be possible, and it's one of the approaches also to look into, because when you say Bayesian belief networks and so on, starting from the data, that would be actually the most straightforward point. So in this case, we start from the control flow. So I do believe that it's possible to combine the two and to add the data perspective also into the control flow. Because now it's mainly control flow based, but I believe they can be combined.
Okay, thank you for your question. Sander?
Thank you, Joche. And also thank you to Gert for the nice and interesting presentation. My question is a bit, actually I have two half questions if Jochen lets me. So the first one is like, how would you, let's say, how could you like evaluate the type of models that you get, and how would it run on real life logs? Could you give us some kind of heads up on that?
Yeah, so we have not tried it yet on real life logs. The difficulty is to try it on real life logs is that the process model that you start from has a certain quality. So we have to find a case where we have a process model and event data that have a certain quality. Because otherwise, if you have a real life log and you do a very simple process discovery algorithm and the model is not of a high quality, then the statistical model that you build on top of it will also not be of a high quality. To evaluate the quality of the, I suppose you mean the Bayesian models?
Yeah, correct. Well,
yeah. There is literature, so there are techniques like the DIC, but also other parameters that tell you something about the quality or the goodness of fit of that model with respect to the data and the Bayesian model that you described, which can be used to compare models, but also can be used if you're using one Bayesian model to test hypotheses. If you're using the different probability distributions, you can also use those criteria to say, or sort of to create a context of how reliable your results are, your conclusions.
Thank you. I think that's a very interesting way. I will probably send you an email offline to okay. if you don't mind to go for that. The second question is you already mentioned it's an R package, so it's maybe more of a, let's say, a fundamental conceptual contribution. However, if you know what you are looking for, like you have a particular hypothesis, wouldn't it be easier? I still see the value of the concept you propose, but wouldn't it be easier to then just go for test that directly on the log?
Well, it depends. I think if you make the if you're going to test it directly on the log, I think that there is a risk that you're going to lose certain nuances in the data. And if you build a complete statistical model, then you take all the process into account, all the control flow. And I think that's you're more safer than just, let's say, computing some frequencies based on the event data. And also what's important is you don't get probability point estimates, but you get distributions. So you have more information to see are they statistically significantly different from each other and so on. So that's one of the important reasons behind the Bayesian approach.
Thank you.
I'm not sure if I come true.
Yes, you do.
Okay. Maybe if I can add something to that also, Sander. I think if you go to test it directly on the log, you still have to do the same thing. You still have to develop a statistical model. I mean, if you want to test it statistically, you're still developing a statistical model, which you then have to test with your data. What this approach does is it makes a translation to a Bayesian model, which is a possible statistical model do the testing. And then you can argue indeed, are you going for a frequentist approach or a Bayesian approach? And both have their strengths, and the advantage of the Bayesian approach is also that it easily allows you to incorporate a person's prior beliefs, which is not possible with a traditional t-test, for example. So you can do that directly on the data, but you're still doing basically the same thing. You're still building a statistical model and using your data to estimate parameters and make draw conclusions. So what this approach does is it makes that translation for you. It automatically develops the model based on the process model, and also relates to the question of Bas. If you want to incorporate the data perspective, I think you have to make a distinction. Do you want to incorporate that automatically so that it generates automatically a Bayesian model that takes into account the data perspective? I think that will be quite a challenge to prevent the Bayesian model to explode. But you could easily say, I take this I take a process model, translate it into a Bayesian model, and then change the Bayesian model to take the data perspective into account. If there's a certain choice where you think here, there's a certain attribute that might have an influence, you just change the distribution of that parameter to depend on some kind of data attribute, and you have incorporated the data perspective. But it will require some knowledge of how to build a Bayesian model. So, but I think it's a very interesting challenge there if we could do that automatically.
All right, thank you. Hans, you have a question?
Yes. Hi. I'm a recent convert to Bayesian approaches, so I very much enjoyed the presentation, Gert. Thank you. My question is actually similar to my question to Mathilde in the previous presentation. It concerns a little bit the seeding of your models, more specifically the prior beliefs that Benoit mentioned. How do you choose your prior, and what is the effect of your prior on your final results?
At this point, we have used always an uninformative priors in the examples, but that would be the advantage of finding, let's say, a real life case with a process model where we also have access to some domain expert, and then we can use in discussions with these domain experts set informative priors about what they think about the different probabilities, and then of course we have to see what the impact is. At this point, because we are mostly using uninformative priors, the impact of the priors is, let's say, neglectable, which means that the Bayesian approach has its advantage at this point in having in returning the posterior probability distributions instead of just point estimates. And the prior distribution setting those at this point, we have not really tested the impact of it yet because we need some domain knowledge there to do that in an intelligent way.
Thank you.
Thank you. Will?
Switch on the mic. Yeah, so also thanks for me for the presentation. I have a bit of a technical question related to the prefix automaton that you are building. You're basically using the same approach as that is used for precision calculations, but there is often the tricky problem that in most of the cases you also translate silent activities, and these silent activities highly influence the result. In your example, you had an end split, but you somehow, it didn't end up in the prefix automaton as a silent activity. Can you tell a bit how you are dealing with this to avoid the typical problems?
So we have an end split just here. We have an end split between D and E. But when we are building the prefix tree, we just look at the event log.
No,
we don't.
I know, and in this
Yeah.
example, it is perfectly okay, but the example looks a bit as if it is made by hand or something like that. If you take a process tree and you convert that to a Petri net, and then based on the Petri net, you build a prefix tree, the prefix tree is covered with silent activities. And these silent activities, they are basically destroying the statistics. That's why the precision measure values are often too positive, because you use alignments, you go into a certain path, and then later it seems as if you had no choice, but you had a choice, but that was resolved by the alignments. Do you see what I mean?
Not really, because we are always going to start from the data. So the model can have silent or invisible transitions and so on.
But Gert, it could be that to decide when you have an escaping edge, you need to take an arbitrary long sequence of silent activities to reach a step that is visible. So it's not clear how you implement that.
Well, not sure what the question is, but at this point, are you pointing towards unfitting traces?
So you are talking about things that are possible in the model, but that you did not observe.
Yes.
Right? If I have a normal process model, not just as an enumeration as traces, then I typically, in my model, I have all kinds of silent activities. Right? So you would need to do a state space exploration to decide what is going to be possible. So most of the people don't do that. They just have a model with silent activities, then they build alignments, and alignments give the path. But then the splits in your model are not based on an activity, they're based on a silent step that was not in the model, etc., etc. So I'm kind of wondering if I would have a Petri net model with silent activities and I would use your approach, it's not as simple as you're showing.
Yeah, I now get where you're going at. So for instance, here after D, F is possible, but it might be that F is only possible after some silent transitions.
An arbitrary long sequence of silent activities.
Okay. No, at this point, we did not really look into that. Another point that's still up for discussion is that the blue arcs here, which are unfitting traces. so we try to follow the model actually as long as it allowed for the trace, and then when there is a deviation, we show it as an escaping arc. That's also, let's say, we show a bias to the first part of the trace. It might be that after this the trace or the case follows the model perfectly, but we consider it as a deviation because we start at the front of it. So that are still, let's say, design choices or assumptions that we take at this point that should be for more complex process nodes or more complex processes that should be looked into. So the aim of this algorithm is to provide a sort of main ID, but there are still a lot of details that need to be worked out indeed.
So a similar problem you would encounter if you would have two activities with the same label that would be enabled at the same time. Then you need to pick one of these activities, and when you pick one, it may be irrelevant what you pick, but only the effect may be visible later, and they have similar issues.
Yeah.
All right, thank you, Will. Bas, final question, but quickly, please, because we are running a bit over time.
Yeah, I can do it offline. It's fine. Because
no, it's okay. It's okay. Go ahead. Go ahead. You can raise a question.
Well, one point that was mentioned by Gert that also relates a bit to Will's question is related to the impact of model quality. So you sketched a bit. You said if the control flow model is bad, then inherently the models you learn will be bad. And I was just wondering whether you could give insights in a bit more detail to whether you can determine this upfront. Like, is there a point at which you say, okay, this model has this quality, hence the whatever I'm going to learn is not going to be of a high quality, yes or no? That's kind of my question.
At this point, we cannot pinpoint it. Let's say the model should have a fitness of 0.8 and then it's fine. So at this moment, we don't really know. What's also another idea is with some modification, you can use it also to discover process model itself. If you, I mean, the theory allows to sort of embed the Bayesian network into a process discovery algorithm, and then you could sort of combine the two, and I mean, you're not solving the problem, but that's also one of the advantages of this is that you can use. It tells us a lot about control flow, but we're not using it to discover a model, but we could use it to do that also, that step.
Okay. All right. Thanks a lot. Thank you very much for the presentation and the nice interaction. I think there was some very relevant questions. So thank you very much to all of you. All right, then we move on to the third paper. Bas, you're going to present your paper?
Yeah, I am.
All right. Go ahead. The floor is yours.
Thank you. You can hear me, right? Let me see. So, can you see my screen?
Yes, I do.
All right. So, indeed, I'm going to present the third paper today, which is entitled The Generic Framework for Attribute-Driven Hierarchical Trace Clustering. So I guess for most people that are familiar in process mining, they from the title already know what we did. Nonetheless, I would like to point out that my co-author, this paper is a product of his master's thesis. So I think that's a very nice achievement from Yukun Kao. Sadly, he couldn't make it today because he decided to leave academia, or decided not to enter academia and go to industry, and had a team meeting, which of course is very important. So hopefully he can watch the video later. Myself, I'm co-leading together with Wil van der Aalst the process mining group of Fraunhofer Institute for Applied Information Technology, where we try to bridge the gap between business and academia, and I'm also affiliated to the I9 chair of process and data science of RWTH Aachen University. So even though I'm not wearing a hat, I usually wear two. Today is September 14th, and let's kick off. So we all know processes, and business process intelligence is all about processes. So let's think about a few examples of a process. Let's think about sending a package from A to B. When we do that, all kind of people, primarily employees of the postal office, will do all kind of things to our package. So our package, when I deliver it at the postal office, will be scanned. Then maybe someone weighs the packet. Then an employee of the postal office picks up the package. It gets into the sorting center, etc., etc. And in the end, the package is delivered at the target destination. Similarly, when I recently bought a house, and when we applied for a mortgage, all kinds of activities were performed in all kinds of inconvenient orders, in this case, finally to decide whether or not I was allowed to get my mortgage to buy the house. So a bank has a set of employees that when we want to loan some money from the bank, when we want to get a loan, will decide whether or not I'm allowed to do so. Again, this is a process. Think of the medical domain where we treat patients, we perform all kinds of activities on top of that patient in order to make the patient better again. And finally, think of, let's say, e-commerce, where actually users execute some process or clients execute some process in order to buy goods, and even the whole logistics of getting the goods to our customers can be seen as a process. So why am I giving you these examples? These are all examples of processes, and when we look at the concept of a process, we could say a process is a collection of activities that organizations perform in order to achieve a goal. And achieving that goal could be to assemble a product, deliver a service, etc. And that's why I like this picture so much in the slide, because it schematically represents the fact that there's a set of activities, 1, 2, 3, that we execute in order to achieve a goal. And this execution is done by humans and by systems. And now these examples that I gave you nowadays, all these different examples that I gave you are supported by information systems such as SAP and Oracle, etc., etc. So all these information systems kind of, within these information systems that these companies use, the bank, the hospital, there's a sort of a digital copy or a digital representation of these processes. And as most of you know, what we try to do in process mining, we try to obtain knowledge and insights of these processes by means of executing, typically automated analysis of the event data. That's the context at which this work that I'm presenting today is focused, process mining. And for those of you that want to have a longer introduction of process mining, please take a look at my pre-video, which accidentally was a bit too long. But what do we do? So within these information systems, there's all kinds of records being stored, which we call event logs, that kind of accurately keep track of what happened in the context of, say, a medical treatment or a package that we send from A to B. In these data systems, there's all these records recorded, and what we do and what we've seen in the previous presentations is we try to, for example, discover a model that accurately represents the process at hand. And what we do is we look at this data, we transform it to some intermediary abstraction, and then we give it to an algorithm, and poof, the algorithm automatically gives us a beautiful model. At least that's how we tend to treat process discovery. And now the question that I would like to pose is, because what we often do is we often say, here's the event log of this process that we're considering. And then we press a button, we press enter. It's like this push button technology, and we run our data set through this beautiful algorithm that we have, and then a model comes out. And the question I would like to pose is, should we merge all the executions of a process into the same model? Should we aim to do that? So why do I pose this question? Let me reconsider the example processes that I gave you. If I go to let's say the postal office, or if I go to a logistics operator and I just start extracting data from a set of days, it's highly likely that the packages that people have been sending in some cases might contain living animals, which need to be treated slightly or even significantly differently from regular packages. And similarly, in some cases, packages might be taken out to check if there's cocaine in the package. The same holds for this bank. If we apply for a mortgage, it might depend on my profile as a customer, what exact steps of the bank is going to execute. Like in my example, I'm living in the Netherlands and I'm working in Germany, which tends to be generating all kinds of side cases for the bank in order to determine whether I am able to get a mortgage. Same holds in hospital settings. So if a patient has a certain, let's say, there's a certain value of a blood test coming out, there might be additional steps be performed, etc. So what I'm trying to say is it's natural that the processes that companies execute differ depending on the context at which they're executed. So a living animal that we send by postal mail, for whatever reason we would do that, might be treated differently. And to some degree, algorithms cope with this, but in a lot of cases they don't. And what happens if you push too many of these variants that contain all kinds of different executions into the same bucket, you get garbage in, garbage out. And why is this the case? It's in some cases, even though for process variant A, activity A is happening in the beginning, and for another variant, it's happening in the end, it can be that the algorithm that we use tends to greatly overgeneralize, because it's simply not able to distinguish or to let's say to apply label splitting. And for this reason, we often get these spaghetti monsters that have been referred to in the previous, in first talk as well. And that's what we try to tackle here in a semi-automated way. So what we try to do in this work is we try to handle this multivariance problem. So there's different variants of the process that lead to different executions of the process that are maybe subtly different, but still too different to result in a nicely interpretable model. Now, one way that I can try to handle this problem is manually. I can say I try to manually split my data, and to say I create a set of sublogs, one sublog representing all patients with these and these blood values, and one sublog that represents all patients with these and these blood values, etc. But this is only feasible, first of all, if I have that domain knowledge a priori, and secondly, if I have a, let's say, if the number of values that we have for the attribute that we want to use to split the data is relatively small. And secondly, there's an alternative branch of work that we can consider, which is learning decision rules, which is kind of saying, okay, if there's a certain choice, that also relates a bit to my question for the previous talk. If there's a choice in the model, is there a data attribute that can drive this choice? But this is kind of a chicken and egg problem in the sense that we, first of all, need to have a good model to be able to apply decision rule mining. So what we did in this paper is we proposed a framework and we tested with an implementation of that framework that conceptually looks like this. On the left-hand side, we see the input event log that is given to us by our, let's say, business partner, or simply that comes from a process. And we also have an attribute that we want to have. And this attribute is typically a trace level attribute. It can be a customer class, a vehicle type, the voltage of a system, you name it. It's an attribute that is recorded at the trace level. And then what we simply do is we split the data according to the attribute. The most simple split would be if the attribute is a categorical attribute, we can just split the traces on the basis of the corresponding values. So if the categorical attribute has, let's say, 20 or let's say 30 different values, we create 30 different sublogs. But if it's a numerical attribute, we can, of course, apply binning. So after this splitting, we have a bunch of sublogs. And in the end, all these sublogs, they form the leaf nodes of a hierarchical clustering that we learn. And what we do is we try to merge within that hierarchical clustering, we try to merge those sets of traces that are closest. And in this paper, we assessed a bunch of different distance functions on a trace level and a set of different aggregation functions that allow us to merge groups of traces on the basis of their intertrace distance. So that's what we implemented and tested with in this paper. We assessed two types of distance metrics So one type was just taking two groups of traces that, for example, represent the same vehicle class, or at some point higher in our hierarchy that we are learning, represent just two groups of traces. One was really a one-to-one mapping of the traces, and for example, using Liebenstein and other types of distance metrics, for which I gladly refer to the paper. Secondly, what we also did for the sake of performance, we did a abstraction first, so we computed the directly follows abstraction of the different sets of traces and then compared on the abstraction level. Those are the two different ways in which we compared groups of traces. As I said, for more details on the exact different metrics that we use, I refer to the paper. And we implemented it in a prototypical implementation that looks a bit like this, where you can give in also in my pre-recording, I have a live demo of this. I will not do that now for the sake of time. But the idea is that you can choose an attribute and then give in a log, and our algorithm will automatically start finding the most common event data, so the most common traces, and merge them together into a hierarchical cluster using these trace attributes as an initial driver. So we did also some experiments. So, and the first experiment that we did was on the BPI Challenge 2017 log, where within every execution of that process, there is a score that is being attached to that instance. So what we did is we took this credit score, and as you can see in this dendrogram on the left, if you look just at the number of individual values of that specific credit score, that's an extremely large amount of different values. So this manual splitting is no longer possible. And so when we then start to do a hierarchical clustering on the basis of this initial partitioning, what you see in this slide is basically, first of all, the whole event log, the model that we get from the whole event log, and obviously it's a fairly simple model to also illustrate how this works, where we basically see that there's two transitions that are always executed, two activities that are always executed, and then there's two skips. So we can skip a middle part and we skip a final part. But then we found out using our clustering that actually that skip is only for those instances of the process that have a score 0, where all non-zero score instances of the process require you to execute the full behavior. And similarly, when we then dive down into our trace attribute driven hierarchical clustering, we see that when the score is, for example, exactly 541, 625, 608, and 634, we see a more sequential behavior, whereas in other cases, there is still some choice in the middle and in the end part. So as you can see, applying this hierarchical clustering driven by, in this case, the score value of certain instances of the process allows us at different levels to verify behavior. So we did some more quantitative experiments. And what we did in this example, we used the open receive phase log. And what we basically did is we started to compute bottom up these clusters of different sets of traces. Again, splitting the event log all the way up based on the trace attribute, and then gradually merging back the most similar groups of traces, so that in the end, at the top of the hierarchy, we have the original event log again. And here we see the average F1 replay fitness and precision score for the models that we learn on the different event logs that we have on the different levels of the hierarchy, starting at the top of the hierarchy. So the leftmost point in these graphs is actually the whole event log. And then gradually we go deeper into the hierarchy that we learn. So meaning we get smaller and smaller data sets, smaller and smaller event logs, more specific towards the trace attribute value that we use as a driver for the clustering. And what is interesting to see, we always compute the replay fitness and the precision with respect to the original event log. And what we see for all the different trace distance metrics and aggregations is we see a sort of a steep increase in F1 score, which then gradually surfaces. And this was what I expected. because in the end, what I expect is when we go down in the hierarchy, we get smaller sets of behaviors. So we expect lower replay fitness and higher precision values. So that was also what I wanted to kind of show that, okay, somewhere in the, let's say, maybe not in the deepest level of the hierarchy, but somewhere below the root, we see this slight drop in replay fitness, but a pretty significant increase in precision. However, what surprised us a lot in these results was actually that the charts smoothens, but it's also dropping a bit again. And this is because the precision is kind of dropping on average, and the replay fitness is rising a bit again. So the blue line signifies this the best, where it rapidly kind of drops in terms of replay fitness and rapidly rises in precision, but then precision drops again and replay fitness goes up. And initially we didn't know why is this the case, but it turned out that there were some outlier cases that were only, let's say, if you look at it from a bottom-up agglomerative hierarchical clustering perspective, on the end of the algorithm were merged into the main branch. So actually what we see is we see the steep drops, because at levels 2 and 3, there's this outlier set of behavior that is quite different from the main behavior that's only then is integrated. And at that point in time, this has a large impact on the measurements that we have, because it's fairly different. So in general, what we see if we look at the results for other real logs is we see the same behavior, although the receive phase log obviously has the strongest behavior here. But again, we see this slight increase of F1 score in most of the cases, showing that in some cases by splitting the data in a smart way, we can achieve models that represent different trace variants. So to conclude, what we did is we sort of gave them this generic framework to drive trace attribute-based clustering, which on the one hand allows you to pre-process your data. So you can slice your data into, let's say, subsets of behavior representing different variants that lead to better models than combining them together. And so it also allows you to create higher level attribute groups in case that the trace variant indicator that you use has a large amount of different values. Our experiments confirm that the splitting actually leads to better models in the lower level of hierarchy with a bit more distinctive behavior that we can see from the rise in precision. And the future work would be very interested to look at the different distance metrics and aggregation methods, because now we use, let's say, Liebenstein, for example, which of course might not be the best metric to compare behavior. And also have been already working with a master student on overlaying the different models of different nodes in the hierarchy, so to really visualize the differences between the trace variants. So I hope everything is clear. I needed to speed up here and there a bit, and I would like to point out that Wednesday, September 16th, we have a beautiful tutorial together with Gert, the previous speaker, on business process analysis using scripting languages, to which everyone here is warmly invited. So thanks for your attention, and I'm happy to answer any questions.
Thank you very much, Bas. That was also a very clear presentation. So again, I would like to ask you to type a Q in the chat if you want to raise a question to Bas. So no immediate questions, then I will start off with the first one. Thank you. Will, okay. Yeah, Will, you can go ahead. Go ahead.
So I can always ask a question. So thanks for the presentation, Bas. You're using a dendrogram to show the organization, right? But isn't it the case that if you are splitting, there may be multiple dimensions that are orthogonal? Let me give an example. I can buy products and I have different types of products. I'm a gold customer or a silver customer, and my order is a rush order or a normal order. So if I have these three dimensions, and then I apply let's say, this approach. And it seems that these three orthogonal dimensions just get blurred in some hierarchy that doesn't capture, let's say, the real essence of the different types. Can you comment on that?
Yeah, I think to some extent you're right. That will be blurred because we kind of flatten. If you have these different dimensions, then two of these three dimensions will be kind of squashed and can potentially be scattered around. Yes, this is correct. And another point that relates also to this is that it can of course also be the case, for example, because on the one hand we use this Liebenstein, and on the other hand also because of noise, it can still be the case that even though theoretically you would have for a given attribute completely different values, it can still be that sometimes due to mistakes stuff is also mixed into different groups. But yes, you're right. I guess those perspectives are then completely flattened and can be scattered around, yes. So in that sense, a multidimensional type of approach would be better.
Yeah. Thank you.
Mohamed Reza?
Thanks for your presentation, Bas. I have a question about your results on slide number 20.
Yep.
So I somehow assume you use the original log for evaluating the quality of each cluster. Am I right?
Yes.
So because you increase the number of clusters, I expect somehow, for example, if you somehow very extremely increase the number of clusters, I expect to have precision 1 and very low fitness.
Mm-hmm.
Do you agree about it?
Yeah, so let me elaborate a bit. These pictures that you see here are cut off, so it's not until the complete depth. Yes, you're right. There are a few side remarks. Precision needs not to be 1. It can still be that in the leaf level you have a sublog that somehow generates, using any discovery algorithm on top of that sublog, then generates a model that when you then use that for replay fitness precision calculation with the original event log, can still have replay fitness 1. This is technically possible. So that's one reason why these values are not 1. Another problem is that I'm not sure whether my explanation was completely clear during my presentation, but there was this outlier group in terms of behavior that got merged very late. And let's say, because these are aggregates and averages, let's say the lower you get into your hierarchy, so the more data points you have to compute the aggregate, the lower the impact of that outlier on the total. And that's why you see this sort of this bouncy behavior. It's because this outlier is always there and will be merged at the end. So in let's say the highest level of this hierarchy, it has a fairly big impact on the quality metrics. Whereas when you go deeper, the impact gets blurred in a way. But this was in general, it was quite hard to think of ways to evaluate the idea in that sense.
And then thanks for your explanation. But I also have another question about the application of your method in somehow real scenarios. So do you recommend, for example, using clustering to having some sublogs, or do you think it is better that the data analyst filter and separate the logs by the business knowledge?
I would suggest, I think personally, a hybrid approach. But also the idea here was, so we always use this example of this gold, silver, platinum clients. And if you have this information and you only have these 3 values, then you should do it manually. But the idea here was there's also scenarios like I showed you where a case gets a score. And it could well be that certain subgroups of scores actually show very similar behavior in other groups than other groups. And I think for those cases, what we showed in this paper is that this is an interesting initial direction to sort of get to aid the user in identifying those differences. And to see, okay, I have this event log from wherever, but within that event log, there's actually pretty clearly, there's classes to distinguish. And if I do that, if I make this split, I really get models that are just of a, let's say, a higher quality than combining everything together. So I think it depends a bit on the case, whether you can do it manually or not. But if you can't, I think having these techniques that we tested here that can support the user to some degree in making this split is can be very beneficial for the quality of the end results of whatever you do next.
Fair enough. Thanks for your explanation.
Thank you. I have maybe one more follow-up question. Did you at any point already compare these approaches with existing trace clustering techniques? Because I can assume that you might find similar patterns even if you don't start with your attributes as a starting point. You can find similar patterns with existing trace clustering techniques, and in terms of your evaluation now, the measures might be similar, or the evaluation, might not necessarily be different with these existing techniques.
Yeah. So we did some comparisons, and those are listed or reported on in the master thesis of you. I think in the example that I gave, let me show. In this example, somehow in the end, I think he used ActiTrack, but he couldn't get this specific splitting. So I guess obviously in the end, these splits will also be in the solution space of any clustering technique that we use. But because most of these techniques, they don't, let's say, take the data, some of them do, but they don't take this data in this way into account. Sometimes they just don't get this exact results. So yes, we did some comparison. In the comparison, we did not get the exact same results. Although I think technically, if you play around a lot with these techniques, it can be the case that you can get similar results, but then you would have to do a post-processing step to find out if there is within the data variables of the different clusters that you find, whether there is a strong correlation between one group or the other group.
Yeah, there are of course several papers that try to integrate both dimensions, so the data attribute dimension and the control flow, into one clustering algorithm, let's say. And there it's all, I mean, it always the question is raised like, okay, what is now driving the clustering technique? So in your case, you make a pretty clear distinction instead, that you start off by looking at the data attributes to select your starting point, and then you apply a control flow driven clustering approach. So that makes it pretty clear. But I think it would still be interesting to see what other techniques do in more detail, both in terms of quantitative results as well as qualitatively, to investigate the clusters like you did here, to see where some differences might exist.
Yeah, I completely agree. That
all right.
should be done as well. Yeah.
All right. Actually, I think this is the exact or a very good timing to give you a short break. Actually, we will not have more than 5 minutes, so I guess everyone quickly gets a coffee. I will stay here. If you want to interact, feel free to interact. But in a little like 5 minutes or so, we'll start again with the next paper. So let's have a short break so that anyone who wants to go to the toilet or go and grab a coffee can do so. And in 5 minutes from now, we will get on with the fourth paper. Okay, see you soon.
Okay, so welcome back. I think it's time to resume the session. So the first paper of this second and last session is process outcome prediction, CNN versus LSTM with attention. And I think Hans will present the paper.
Yes.
So Hans, the floor is yours.
Thank you. Are you seeing, am I sharing my screen or not?
Yes, you are.
Okay, excellent. All right. Good morning, everybody. I hope you enjoyed the previous presentations as much as I did. My name is Hans Wijtjens. I work with Jochen, and as Jochen already mentioned, we're both at KU Leuven in Belgium. The previous presentations so far, they all dealt with process discovery. Here, we're going to take a different, we're going to be looking at something else. We're going to be looking at process outcome prediction. The presentation is has a traditional structure. We're gonna first show you the key contribution that we made. Then I think it's probably worth positioning our paper amongst the body of current research to give you a feeling where we are and what we're doing there. Then I'd like to show you the models that we are using to give you an understanding of them before walking you through our observations and our experimental evaluation. And then we're going to arrive at some conclusions and formulate a few suggestions for future work. Well, the key contribution basically is that we empirically demonstrate that convolutional neural networks, and I'll come back to those, are fast and robust alternative to long short-term memory models in process outcome prediction. And this applies both to completed and to ongoing processes. As I said before, I'd like to spend a few moments on positioning our paper. There's a whole body of research actually in this area. The traditional machine learning techniques have been applied successfully on these problems. A very good example is the Tanema study. She did a large benchmarking study. Then neural networks made a showing on the scene, and Everman, who's possibly in the audience here, Tax Camargo, they were first to apply LSTM to next event and time prediction models or predictions. So not quite outcome prediction, but more or less same thing. Hinka, he was the first to apply LSTMs to outcome prediction, the problem we're going to be looking at. Kratch then compared LSTMs to classical machine learning. And then Wang added the attention model, which I'll explain in a moment also to this body of research. Now, the interesting thing is that none of these researchers contemplated CNN models for outcome prediction problems. Now, convolutional neural networks, or CNNs, they were originally designed for spatially organized data, for example, images. But in the one-dimensional form, they also proved very, very useful for time series classification and sequence modeling, so that I can actually deal with this kind of problems. Fawaz, for example, he did a large empirical study in time series classification using these models. So we thought, okay, maybe this is an interesting approach. Maybe we can try that to process outcome prediction. We found one study that used convolutional neural networks for next event prediction, not quite the same kind of problem, but interestingly enough, they used the two-dimensional form, which is maybe not the intuitive approach there. So okay, as I said before, we're going to be including CNNs in our evaluation. We're going to be looking at LSTM with attention like Wang did, and we're going to be concentrating on outcome prediction. And we'll also have a look at early prediction, because of course it's very easy to say what the outcome of a process has been after the process is completed, but we also want to see or predict what's going on before the process is completed. Okay, our models. Let's have a look at the models first. And before we do that, actually, we should also have a look at how the data is presented to these models. So for all of the models that we're going to be using, we have to organize the data into sequences of events. A sequence that has 2 dimensions. There's a sequence length. Are we looking at 5 events at a time, or 10 events, or 20 events? And of course, the second dimension is the number of features that describe each one of these events. Now, how we're going to be doing that? We're basically going to be sliding a window over all of the events in a case. I hope you can see that in the graph. We have a case that exists of
16 events, which are described by 3 features each, A, B, and C, and we slide this 9 event window over the whole trace, thus generating a whole bunch of matrices which are going to be presented to the models. The first model is a plain vanilla long short-term memory model. I think most of you will be familiar with it. The main point here is that the events or the sequences will be treated in a sequential way. So basically the information is being passed from one time step to the other. You can follow the red line here. Information here is collected from the lower levels. It's passed on to the next time step, to the next time, and so on. Finally, we'll reach the end of the sequence, and an output is generated that's being presented to the next level in the model. Now, the problem or the potential problem with these plain vanilla LSTM models is that you see this red arrow is very low. All that information is contained in a vector, basically. The risk here is that when the number of time steps accrues, that some of that information is going to get lost. That's where attention comes into play. That's a more recent invention, let's say. It's the same when applied to LSTM. Basically, the underlying principle is the same, but at every time step, we're going to record the results here. And then at the end, we're going to score all of these results. And then based on that score, a kind of a weighted average is going to be computed, which is then passed on to the next level. So the idea here is really to retain the best information, to not lose information during the progress through the sequence. Next are then the convolutional neural networks. As I said before, they were originally designed for spatially organized data, images, but they have been successfully applied to one-dimensional problems too. And here, the one-dimensional problem in our context is the temporal axis. Of course, we're going to be looking at events that happen in a chronological order. CNNs are able to automatically extract a hierarchy of patterns. When in the example here, we have 2 filters, as they're called. You can see that here we have 2 filters. We use a stride of 2, I'll explain, and the kernel size is 3. So basically, we're going to be looking at 3 events at a time, and every observation is going to be 2 time steps away from each other. That's that stride of 2. So this way, we're extracting information to the next level, and again, it's kind of a hierarchy of patterns that we are trying to discover here. The interesting thing or the difference with these LSTMs is there's no chronology. We're not going from left to right here. Basically, we're taking a helicopter view. We're looking at all of these events or windows of events at the same time. So that's a big difference. That's why nobody thought of using CNNs for time series problems originally, but it turns out these things work pretty well. So we're now ready to look at our experiments. Yeah, maybe a few words about the data sets we used. We used 4 data sets. Most of you will be familiar with them. BPI'20 2012, 2017, traffic and sepsis. Well, all of those are publicly available, of course, which makes it easier for comparison reasons with other papers. Interesting to note is also that the BPI'20 2017, it's about a loan application process at a Dutch bank, is very similar to the 2012, but it's larger, it's of high quality, and there's more features. And that's important to know, to remember that, because the results will be very different as well. Our approach is rather traditional as well. In pre-processing, the most important pre-processing steps are probably the creation of time-related synthetic features. With those, I mean, for example, the day of the week, or the time since creation, or the time or since the start of the trace or the case. also very typically, we mapped our categorical features into integers, and then they were used, yeah, an embedding layer was then used in the neural networks. But basically, it's important also that we tried not to optimize these problems. We were not after the best solution for all of the problems that we have. Our basic goal was actually to compare the models and the methods with each other. So we did not add any further human knowledge other than these time-related synthetic features. We did no sampling to correct imbalances amongst the targets. Some of these databases are highly imbalanced. Yeah, so the same approach for all of them. We set aside a test set of 20% of the cases to test our results. And then we used early stopping based on a validation set of 20% of the remaining samples. We did some hyperparameter tuning. I'll come back to that when showing the results on that. And then the metric that we used is the area under the curve, which is a logical choice maybe because accuracy would not have been possible given the imbalance of the targets in some of our data sets. So now to the observations that we made. First, most important one maybe is that the CNNs perform in line with both kinds of LSTM. The gray bars here are the LSTMs, the white ones are LSTM with the attention mechanism, and the CNNs are red. So you can see visually within a second, in an eye blink, you can see that the performances are nearly identical. There's no statistical difference. But here you can see that BPIC 2017 compared to 2012 performs a lot better, about 10 percentage points, which is a big difference. You can also see that traffic performs reasonably well, but sepsis, this database or these data sets are characterized by small, they're pretty small, and there's a large number of features. So these neural networks, they struggle with this kind of problem. Second observation, I think for the practitioner, a very important one is that the CNNs train much faster than both kinds of LSTM. They're about 5 times faster. It's like half an order of magnitude. So given the fact that the results are more or less the same, they're much faster, that's a very strong incentive, I would say, to use CNNs rather than LSTMs. We only looked, by the way, at training times to predict, but the prediction times by themselves are irrelevant. They're very small or quick. It turned out, because we had 10 learning problems distilled out of these 4 data sets, it turns out that the best models within the hyperparameter space, they were always using different values for these hyperparameters, which is maybe at first sight a little bit disappointing because there was no clear indication which hyperparameter value was ideal. But then on closer inspection, it actually turned out that these models are very robust with respect to these hyperparameters. So the results don't vary much. You can see here on the graph that we tuned 4 hyperparameters: the batch size, sequence length, the model size, and then for CNN only the kernel size. So here it's between 79 and 80. You see that these results are extremely robust, at least as long as you stay within a reasonable range for these hyperparameters values. Yeah, as I mentioned before, we obviously don't want to look at finished cases. That's too easy. The result is known. It turns out that here we sorted our data set according to the prefix length. And here we see that for very short prefixes, 3 to 4 events only, we already reach maximum predictability, which is an interesting observation. It actually means 2 things. It means that a lot of the crucial information about the outcome of these processes is already contained within the first couple events. So actually after 3, 4, 5 events, one already knows what's going to happen at the end of the whole case, which could last for a lot longer. The second observation is also that these neural networks are able to pick up that early information, which is good news. So it is possible, these graphs show, to pick up, to make early forecasts. Early prediction is possible. The last observation is not is a question really. When working with these data sets, well, we see that early predictions are possible. We see that CNNs, which are actually designed to work with spatial information, the timing of the events is maybe less important in them. We start wondering, do these timestamps really matter? Because the field of process mining is actually defined by the fact that there's timestamps available in the data sets. But looking at this, yeah, we really start wondering. The left on here on the left side, we see the best model that we used for all of our 10 problems. Here on the right hand side is the average of our models over the total hyperspace. There's no difference between the two, so let's look at the left hand side here. The gray bars here for LSTM, attention, and CNN, the gray bars here are the results as presented before. Now, when we take away these synthetic time features, like day of the week or time since start of the case, our results actually improve, which is very astonishing. Basically, by getting rid of that time information, we have better results, or at least our results are as good as before. The red bar may be less interesting, but when we get rid of the event number, because we numbered our events from 1, 2, 3, all the way up to the number of events in the trace, getting rid of these event numbers also did not change the results at all. And then we tried something else. We just shuffled the events within the traces. So basically getting traces with nonsensical sequences of events, and you see that here in these bars with dots. Again, no significant change of results. So here the question arises, we've only done this for BPIC 2012, so this may not be applicable to all the data sets, but at least it seems that there are data sets in there that are very often used in the process mining environment or research, I'd say. These timestamps don't seem to matter all that much, or we're not able to really pick them up. It's a side question. We could not formulate, or we did not try to formulate a real answer to that. So let's summarize what we observed. Basically, the main point is that neural networks, we're talking about LSTMs and convolutional neural networks, they do work for process outcome prediction, provided, but that's nothing unusual, sufficiently large data sets, which also, by the way, if you're an organization looking at using these kind of models, do start collecting your data in a high quality way sooner rather than later. CNNs are much faster than LSTMs, so we see, yeah, there's a very strong incentive to use those over the LSTMs, which may be the intuitive choice to use. The attention mechanism, contrary maybe to other papers, but we could see not much added value. Fortunately, for the practitioner, these models are very robust to the hyperparameters, so it doesn't matter all that much if your hyperparameters, I mean, if you don't have time to spend tuning your hyperparameters, if you choose reasonable values, you're going to get good results. And then early predictions are possible. So that brings us to a few ideas for future work. The first one is that, of course, this work can be extended. We did our early outcome prediction, but we can extend this work to next event and duration prediction, like some of these other papers that I mentioned in the beginning did. Of course, as always, you can try to generalize the results to a wider range of data sets to prove the validity or the width of the robustness of the results. Something else that we were thinking, but it's also probably not new to the process mining community, is that it's very hard to compare the results of your own work or of other with the work of other people or other research. There's just no framework for comparison. people use the same data sets, but some of them the pre-processing will usually be different, the models will be different, so it's very, very hard to compare these results, which is a pity, really. This question that we raised about the irrelevance of timestamps, maybe somebody wants to look at that to see if that's really an issue, because that would be, especially within process mining, a strange result to have. We didn't make the effort also because it's so difficult to compare things, to compare our methods with the traditional pre-neural network methods. Another classic of neural networks is that they really do look like black boxes. So there's definitely value in trying to get some insights on how these models work and how they reach their conclusions, and then maybe also reaching insight in the certainty or uncertainty of the predictions would also probably facilitate their application in the real world. Managers or practitioners need to have confidence in the results of the models that they're using. So that's our presentation. Thank you much. Thank you very much for your attention. And yeah, I look forward to your questions.
Thank you, Hans, for your nice presentation. So we can use the same mechanism. So if you have any question, you can type a Q in the group chat. Okay, I see that Mathilde has the first question. So please.
Thank you very much for your presentation. I have a question. When you say you shuffle the event, so you mean that you lose the order of the event, so you don't have the sequence like trace. I mean, the trace are not like a sequence, right?
Correct. There's no more order. Basically, the order is nonsensical. You can start with the end and end with the beginning.
Okay, then I have another question. So you say that you compare the conventional neural network with the LSTM, and it's good because it's faster. But then I wonder if the result would also be good with like classical machine learning. So it would be nice to have a comparison.
Yeah, as I mentioned before, it's a little bit hard sometimes to compare results. We had a look at, or we actually extensively looked at a benchmarking study done by Tanema, and in the beginning tried to compare results. This is probably possible with a little bit of effort, but Tanema, she used subsets of the data sets, etc. So it's a little bit hard. And this is actually the main problem, or one of the problems that I think we're facing in the process mining community. It is hard. But intuitively, we did a little bit of comparison, but I did not publish the results because they're not 100% comparable. We are a few percentage during the using neural networks improves your results by 2, 3, 4 percentage points, I would say, compared to traditional methods on the data sets that we used. But again, it's a little bit hard to compare. That's why we did not publish these numbers.
Okay. And just one question that I didn't get. What is the ATT? The bar chart?
ATT, sorry, that's the abbreviation for the attention mechanism.
Okay, thanks.
Yeah, the attention mechanism that I explained here.
Yes.
Yeah, okay.
Okay, thank you. Bodwin?
Yeah, thank you. So can you explain to me a little bit, because I'm puzzled by your comment that the time does not matter. My intuition is that this is because you're training your network in the wrong way. You should make sure that your training data is fully temporally separated from your test data. Right? And if you don't do that, especially in some of these data sets, there is, for example, batching, there are delays that can be trained by a neural network, but they will only happen in the future of the current event in the test set. So you're actually using information from the future of the current event to predict the time for the current event. And this would be one explanation why you see that the time aspect doesn't really matter much. Could you comment on that?
Yeah, I'm not totally sure if I understood the question correctly, but I don't see how we used, well, basically we train our models on cases or subsets of the cases, and then the LSTMs they basically these models run through that information through these available information to then make a forecast of the outcome of that process, which can be immediately thereafter or many events later in the future. So in that sense, I don't really see how we incorporated the future information within.
Well, think for example of the road fines log. It's a good example. So this road fines log has a number of batches in there, right? Moments in time when suddenly dozens or even tens of dozens of cases all at once get sent to the prefecture for appeal.
Okay.
And or for credit collection. And these batches, they do not happen at a specific point in time. They're completely random over time. So if you make a prediction for an event, you cannot predict when this batch will happen. But if your training data contains the next batch, you will predict the position of that next batch correctly. And you'll get a very high accuracy on predicting this will happen. And your network will have learned this from the training data because it has information from the future. Do you see my point a bit? It's a mistake that every single prediction paper so far makes. So it's very common, but it does explain why these neural networks tend to be so incredibly good.
Well, I'm not really sure. You're using the example of the traffic. These observations about timing were made about the BPIC. So this, the observation that you made that these credit collection files, or whatever you want to call them, are sent in batches to the credit collection facilities, doesn't really apply there. So I'm trying to understand what it. How your comment could apply to our work, but I don't really see it. Yeah.
I would probably suggest that you take this offline, so we give room to another couple of
no,
questions.
I'd be happy to. Yeah.
Yeah. So Gerd.
Yeah, thank you, Hans, for the presentation and for the paper. Could you elaborate a little bit more on how the input of the CNN looks like? Because normally the CNN is mostly used for image recognition.
Correct.
So you have a two-dimensional image, and then you have a depth with the different channels of the colors. How do you use that for how do you do process data? How do they fit in that?
Well, basically, we reduce one dimension. There's only one dimension. When you look at an image has two dimensions by nature, and then there's three channels for every one of the colors. Here we reduce this to one dimension. That one dimension that is left is time. So basically, when you look at the slide here, I hope you see it. You still see it, yeah. There's only one dimension left, which is the sequence, of events. So we're going to take samples. We're going to apply our filters at different positions along that one dimension which is left. But every one of these time steps still has three features. So don't get confused. The one dimension is for applying the filters, but every filter will still look at the three, or in this case, three different features that we have to describe these events. So there's only one dimension, that's the sequence of events or input. Does that answer your question?
Yeah, so it's comparable to an image, but you don't have different channels. You just have one two-dimensional.
There's only one dimension. There's only one dimension, which is time.
Yeah. Okay. Yeah. Thank you.
It's very commonly used, actually. As far as we know, it's not been used in the process mining area, but in other areas, it's been used quite often in recent years, and with success, one should say.
Okay, thank you, Hans. Will?
Yeah, so I would like to follow up a bit on Boudewijn's question. So if you look at processes, then often, let's say, the outcome of a process is depending not so much on the case itself, but on other cases. For example, I flew back from Italy yesterday. It was a complete mess in the airport. Whether my bag is going to be on the plane or not, it was luckily on the plane, surprisingly. But whether it's on the plane doesn't depend on the weight of my bag, the color of my bag, etc. It depends on the number of other bags. of course, there are applications where such phenomena do not play a role, right? Like if I look at your figure 5 in the paper with the performance results, they are kind of all a bit similar. So my question,
page 5, you said? No.
No,
the fifth conclusions.
In the paper. No, where you compare this, right? Yeah. So here, the performance of everything is rather similar, right? Whatever you do.
Yes.
But can you then explain to me, if you switch off time and order, what are now the characteristics that influence the prediction?
Well, I didn't look into that in the utmost detail, but before we already observed that early prediction is possible, that after 3 or 4 events already, you can make a very good forecast about the final outcome of the case, which suggests that, but we didn't make it explicit, which suggests that in this case, there is some form of information, something that happens early in the process, and then basically you know it all. So that is a little bit, I think, what's behind that. Then the timing doesn't really matter. If this event happens, yes or no, then the outcome of the case will be this or that.
But
this is my intuitive interpretation. But again, this is more a question than an answer.
Yeah, maybe because it would be important. Like if people would like to apply something like that, they need to, in the end, understand what is now causing these differences. And so it could be that there is a hidden attribute, which is actually already the answer.
But this is always the case, Will. In every model you're going to be using, there's always the possibility of a variable that explains other variables, but which is not in your data set. No? This is unavoidable.
Yeah, and therefore important to investigate.
Exactly. That's why we have in the future research.
But I'm trying to say we should, when it comes to predictions, we should get a bit out of the number comparison game, because like if people in the end want to apply this, we need to have a better understanding what is now driving this.
Correct. I think this is a major issue, not just in the process mining, but these neural networks, they're black boxes, and there's more and more research, but it's very hard to open these black boxes and to understand what's really going on. If you're applying for a loan and your loan is denied to you, you want to know why that is, and that is very key. That is important. Research.
So if you use old-fashioned logistic regression, you know exactly. Right?
Yes, but this is true. But that's why, amazingly enough, one of the approaches is to use neural networks to make predictions, and then based on these predictions, you're going to make a simple regression model that you then can use to explain the models that your neural network has made. It's one of the approaches which is actually crazy if you think of it. You're going to make a complicated model and then use a simple one to explain the complicated one. Yeah, it's a very interesting area, very, very relevant one.
Okay, so thank you again, Hans, for your presentation. I see that there are a couple more questions, but we're already 5 minutes behind schedule. So sorry, Benoit and Ingo, but I think we should just move on.
But how do we do that? Is there a way to do it later, or is there can we do it? The coffee breaks were meant to do that. If people have questions, how can we do that?
Yeah, I think so. So Benoit, Ingo, please approach Hans.
Yeah, or send me. All right. Yeah. Thank you.
Okay. So Hans, if you stop sharing, then we can move to the last paper of the presentation, which is improving the state space traversal of the ESD miner by exploiting underlying log structure. And I think Lisa will be presenting the paper. Yes, so the floor is yours.
Thank you. Welcome to the presentation of our paper. This paper is based on the master thesis of one of our students, Yannick Epstein, who unfortunately decided to not enter academia as well for now. I'm still trying to convince him. And as Andrea already said, it's about improving the state space traversal of the discovery algorithm EST miner by pre-analyzing the log to guide the traversal. I don't have to really introduce process discovery again. We take an event log as input, and as output, we get a process model, which in case of the EST miner is a subclass of Petri nets that has one transition for each activity in the log, meaning that we have in particular no duplicate or silent activities. And this means that our discovery is focusing on discovering the set of places connecting these transitions. So the advantages of the EST miner is that we can guarantee the local fitness for the traces replayable by each trace. We can also have high precision. In particular for this subclass of Petri nets, we can guarantee maximal precision. We can find complex control structures like long-term dependencies, and we also have some integrated noise handling. On the downside, we have some troubles with global fitness. We have some trouble with simplicity of the returned model, so they can be very complex, like for most language-based region approaches. And we have a very long computation time for the algorithm, which is made up of 2 steps. The first step is a state space traversal where we discover the places. And the second step is the remove of the place, which I'm going to explain now. So the basic idea of the algorithm is that
Lisa, I think we lost your sound. Am I the only one who was not able to hear properly, or?
No, no.
Okay. I also lost sound. So, Lisa, maybe, I don't know, try to mute and unmute. Or...
I think Will is going to tell her in person.
Okay, because you're at the same place, right?
Yeah.
Okay.
Work. Hello?
Yes.
Yes.
Much better now, yes.
Okay, I have no idea why it is better now. I hope it stays better.
Yeah, as Bas suggested, maybe the ESD finished the computation. Okay, so please continue.
Yeah, where was I? Exactly, so we want to find the set of all possible places that correctly replay the event log and enter them in our Petri net. And if we want to evaluate all possible places, we run into the problem that if we allow for arbitrary initial markings, this is going to be an infinite set of possible places, because basically we can just keep adding tokens and get more and more places. So we solve this problem by adding a starting transition and ending transition to each trace, and requiring that in the beginning of replay, we have a token in front of the starting transition, and in the end of replay, only the place after the final transition is marked, which means that all the places that we want to evaluate are empty in the beginning and end of replay and are purely defined by the set of ingoing transitions and set of outgoing transitions, which means we can represent it like this, with start being the ingoing transition here and A being the outgoing transition for this example place. And then we evaluate them by replaying the log, one trace variant after the other. And you can see that for this example place, the first trace can be perfectly replayed. So there's no missing token during replay, and after replay of the trace, this place is empty as well. For the second trace, this is not the case because there's a token remaining in the end of replay. And in this example log, you can see that the first trace occurs 99 times, while the second trace only occurs 1 time, which gives us reason to believe that the second trace might not be that important. And we make use of a noise threshold, tau, which we make user definable. So in this case, with a noise threshold of 0.9, this means that a fraction of 0.9 of the traces should be fitting for the place to be considered fitting. And since for this place, this is true for this event log because the first trace is fitting, we consider this a fitting place. Now, if we do this for all possible places, which are exponential in the number of transitions, then we are going to take a very long time. So we try to be faster by skipping certain transitions. Can you? Yeah. If we consider this place, but at another outgoing transition, as indicated by this blue line, we can no longer replay the first trace because we put a token here, which is consumed by the transition A, and then we want to execute B, but there is no token left to be consumed. So we call such places underfed. And since it is underfed for a very large fraction of the traces, this is not a fitting place. Now, if we consider this place, which we create from this place by adding yet another outgoing transition, we don't even have to replay our log because we already know that this place had too few tokens. So by consuming even more tokens, it's not going to be fitting. So we, instead of evaluating this place, we just cut off this connection and already discard it. Similarly, for places created by adding ingoing transitions to an already evaluated place, in the end, for this place, for example, we have a token left in the end of replay of the first trace. So it's not a fitting place. And if we add another ingoing transition, of course, there are more tokens going to be left in here. So we already know without evaluating that this is not a good place, we cut it off. Now we want to apply this idea to the whole search space of all possible places and cut off places in an effective way. We do this by organizing all the possible places. So these are all the possible candidates for this small example log. We organize them as a set of trees with the places that have few transitions in the first level as roots of the trees, and then the places that have more transitions added as children of these roots or descendants of these roots. And if we keep all these place candidates in memory, this is going to exceed memory for larger logs on most systems. So instead, we just keep one candidate in memory at a time and have a deterministically computable rule of how to traverse to the next candidate based on the current candidate. So if we evaluate one candidate and it's unfitting because it's underfed, for example, it doesn't have enough tokens, the rule would say that the rule says we apply depth first search on this whole set of trees. So from here we go down this subtree, then we go down the next subtree. And if it's underfed, we just imagine we would have already traversed the blue subtree and proceed with the next subtree. And this way we can cut off subtrees and thus large chunks of the search space. And the algorithm will be much faster than if we really evaluated all the possible candidates. One problem is that So one good thing is that we find all the fitting places, meaning that we achieve maximal precision. Bad thing is that we find places like the one marked in red, which is not an incorrect place, but it doesn't add any constraint or information to the trace that you can see depicted by the other places below. So to remove such places which are cluttering our resulting model, we remove, they are called implicit places, and we remove them in a pretty time-consuming post-processing step. And as you remember, the trouble we had with this algorithm is, on the one hand, the complex models, on the other hand, the very long computation time, despite cutting off subtrees for state space traversal and implicit place removal. And in this paper, we want to present some ideas on how to be faster and return more simple models. We do this by guiding the traversal through this tree structure for the first approach in such a way that we cut off larger parts, larger subtrees. For the second approach, we introduce additional criteria for cutting off subtrees, which are added to the underfed and overfed cutting of subtrees. So in principle, for such a set of activities, this tree is always built in the same way, always traverse depth first search, but we can change the order in which we add activities. So for example, in this case, here we add, after this candidate, we add the outgoing activity B first, but instead we could also add the outgoing activity, the end activity first, which would organize our places, place candidates in a different way. And if we put candidates which are overfed or underfed very close to the root and give them a lot of blue or respectively red children, then we can cut off larger parts of the search space, and thus hopefully we are faster. And this is what the first strategy is doing. And to this end, we introduced some metrics on the event log and tested several ways of how to achieve this goal. The first three metrics use a similar strategy. So the first metric was just counting how often an activity occurs in the log, which is absolute activity frequency. The next metric is the absolute trace frequency, counting how many traces containing the activity occur in the log. And finally, the average trace occurrence, which computes how often an activity occurs in average per trace. And all of these are used to increase the likelihood of underfed. So we use all of these to choose the ordering in such a way that the places which are likely underfed are closer to the root by adding the very frequent activities first, because they are likely to consume many tokens. So if we add them at outgoing activities first in the tree, then those candidates are likely to be underfed. Also, if you look at
Lisa, the sound seems to be gone again. Lisa?
She will come and use my laptop.
Okay.
Yeah.
Nice background picture, Mohammad Reza.
Eindhoven.
So do I understand correctly, Bas, that the updates from Windows are starting to happen in Germany only today? Or they happened here over the weekend?
I guess we're a bit behind.
But it shouldn't update while someone is presenting.
But it's Windows.
Touché.
Yeah, indeed.
I mean, typically these things are controlled by some university administrator who has no idea that there is a conference.
That's distributed here, so we have an administrator per group.
So can we get a status update, Mohammad Reza, about what's going on?
His computer is also updating.
So they can hear me. I don't know if it works.
Yes, we can hear you now. Oh, and we can see you too.
Perfect. Unfortunately, my computer is crashing down. I do not know why yet, and I sent my presentation to Mohammad Reza, but it's not here. So maybe I just keep explaining without presentation until it is here, so we don't take too long.
Actually, in your other session, the presentation was fine. So maybe you can just ask someone to push the next button on the other presentation.
Okay, I will ask him to.
So this is one of the occasions that you're very happy that you did decide to wear clothes for a virtual meeting.
Yes.
Okay, so to be a bit faster about this, so we don't run out of time too much, we have this final metric, which I didn't explain yet, which is based on the average first occurrence index of an activity within a trace. And obviously, the earlier an activity in a trace occurs, if we put it as an outgoing activity, the more likely the place is going to be underfed. And we make use of all these metrics to organize the places in the tree in such a way that we cut off as many child subtrees as possible. And Mohammad Reza, if you show the next slide, please. So if we just keep going until the evaluation. Yeah, here. So if we evaluate these different strategies, all of them are faster than the lexicographical ordering. So on the left side, you can see the percentage of the running time on the lexicographic ordering. And the most efficient or the lowest running time consistently is for the average first occurrence index for the repair log, road traffic fine management log, and also a subset of the step system. So this seems to be working best. And for this approach, we get the same model as the original approach because we basically still evaluate all the places that we could evaluate and that we don't know to be bad ones. But it's still pretty slow, so we introduced the second strategy, which is adding an additional cutoff criteria. Next.
which is based on the assumption that if you have a very low fraction of traces where the activity A is eventually followed by the activity B, then the connections from A to B are uninteresting. And we can use this for pruning all the places that make this connection. So for example, here you see circled in red a place that is connecting A to B, and then we can cut off all subtrees of this place because all of them are just getting transitions added. So they are also going to have this uninteresting connection. Next, please. We implemented this using an interest score, which we define for each set of pair of activities, in this case for AB, based on the fraction of traces that make this connection compared to the traces that have both activities. And for each place, we just take the minimum of all these scores for all the connections they make, ensuring that we have a decreasing score the lower we get in the trees, and thus we can cut off the subtrees by knowing that the score is going to be lower. Next, please. And if we do, so we have an additional threshold, an additional parameter lambda, which is also definable and says how many traces we want that indicate that there's no relation between A and B to be allowed to cut off this connection. And if we put that to the maximum, which is 1, saying that as soon as there's an indication that this connection should not exist, then we get very fast compared to the original approach. And this, you can see this evaluation again, where we get below 5%, but mostly below 1% of the original running time without this additional cutting criteria. But of course, we do no longer guarantee that the same model is returned to the original approach. Next. So if we compare the model returned to the models returned by the original approach, the original approach is shown in blue, and the model is shown in orange for fitness and precision. Then we can see that the values are changing, but only slightly for different values of the noise parameter tau. So if you have higher values for the noise parameter, they remain pretty similar. So model quality seems to be comparable for the tests we performed. And also we can still find long-term dependencies because we take this eventually follow relation into account. Next, please. Yeah. So to conclude, the first strategy was reorganizing the search tree, which returns the same results in 60 to 80% of the original time. And the second strategy was additional subtree, which returns comparable results with a search for places in less than 5% of the original time. Also, because we cut off many more places, we get a lot less implicit places, meaning that the implicit place removal takes less than 0.5% of the original time, and the whole approach becomes much faster. For future work, we would like to investigate more evolved heuristics for the ordering of the tree, but also for the pruning criteria, and investigate the relation between the noise parameter tau and the pruning parameter lambda. Also very interesting would be the combination with other existing variants of the ESP minor, for example, with the uniwired variant presented last year, which also made the approach much faster, or with the implicit place removal introduced recently, which removes implicit places by replaying the event log on the places. And yeah, that's it. Thank you for listening, and sorry for all the interruptions.
Thank you, Lisa, for your nice presentation. Again, if you have any question which is not related to the operating system of Lisa, please type a Q in the chat so we can start the question session. Yeah, Bas, please.
Yeah, Lisa, thank you very much for your presentation. I have a question also a bit related to performance of the algorithm. so I was looking at the paper, and you mentioned like it's the basic algorithm is exponential in the size of t transitions, which is, I guess, the same as the number of activities in the log.
Yes.
Right? Because every activity refers to a transition. But what's interesting is, okay, so when I look at time performance, we see that for the road traffic fine management in your experiments, you also have the table in your slides. You go from 3,000 seconds to 12 seconds, 13 seconds. But for sepsis A, it's well below 1 second. And it has 2 activities less. And I'm now talking about the optimized version. So it seems that obviously the optimized version remains having this exponentiality. And I was wondering, from your experiments or from your experience, what is the current limit of activities that your algorithm can handle?
So in principle, of course, that depends on how long you are willing to wait. I have never waited more than a few hours. And if you want to limit the running time to minutes instead of hours, with the original approach, you should not go to more than 11 or 8 activities. With this improved approach, we were able to run it in less than a minute, up to 20 activities for some logs. But as you already said, it doesn't only depend on the number of activities, but also on other properties of the log. It really depends on how much information we get to cut off subtrees. So if it is a log that has very few activities compared to others, but doesn't give us any information to cut off subtrees, we are still going to take longer. If it gives us a lot of restriction, then even for more activities, we can cut off larger parts and be faster. Okay,
and so follow-up question. So in any case, there is a set of activities for which you would be fairly fast. Now, I can see great value in combining your approach with like inductive minor. For example, to enrich certain subparts of the tree. And my question would also be, do you have a feeling whether or not there are certain indications, for example, you could get from sublogs or directly follows graphs somehow to make the decision, okay, in this part of a process, or let's say for the model based on inductive minor, it would be interesting to also apply my technique or something like this?
So inductive minor, the basic version is focusing on a very simple subset of control mechanisms like choice, parallelism, and sequence. And it doesn't really it doesn't have long-term dependencies, but it also doesn't introduce any control mechanisms that, for example, in a parallel construct say that the parallel construct one construct has to run to a certain point until the other one can proceed, and complex control mechanisms like that one. So I think if we use inductive minor to find all the more basic constructs, the basic blocks, then we can plug in my algorithm to avoid something like the flower model fall through or similar fall throughs, and find a nicer sub block.
So like an EST fall through in a way?
Yes.
Okay, thank you.
But I also think that I could use other algorithms as input to get a feeling for interesting connections, because they are usually very fast compared to my algorithm, and use these connections to somehow guide the search for places or to improve the model given on the skeleton model that I already have.
Thank you, Bas and Lisa. I actually also have a small question, which is about the different heuristics that you have, and what's the effect that those heuristics have on the models that you extract. from a more qualitative point of view? I mean, you mentioned in the related work that you're planning to investigate different or new heuristics, essentially. So could you think about heuristics that are less affecting the results? Because I would assume that those are what you would like to have, right?
Not necessarily. So your question is kind of, I think, implying that there is a perfect model that we know about and that we want to discover somehow. But very often I think that the perfect model that you want to discover depends on your situation, on what you are hoping to achieve using that model. So
I'm sorry, I'm partially agreeing with you in the sense that I think that you would like to discover a model, or better, I think you don't want that the model that you discover is affected by the heuristics that are used to explore the state space. Those are things that I think should be just behind the scene of the algorithm. So those are just, you know, computational optimizations of the algorithm. So I agree with you that the perfect model does not exist, but I don't think that the model should be affected particularly by the mechanics of how the log is mined. If you see what I mean.
I'm not sure. I think basically the model is always going to be affected by the discovery algorithm that you choose to find it.
Yes.
And for my algorithm, I would say that depending on how you configure it, you will always get a slightly different kind of model, which might also be a good thing, because then you can tweak the model to achieve what you want to have. But
so, okay.
It's a collection of very similar algorithms.
That's a fair answer, I think. So you're assuming that the different abstraction functions are sort of different notions of noise or different notions of abstraction that you can just plug into your algorithm. That correct?
Exactly. Or for example, for the pruning now, I just said that I consider certain connections to be interesting because they don't appear in the log, but one could also get information from different sources. In interactive process mining, you can get some user input, or you could get some information on causal relations that are mined by other algorithms. So you can kind of plug in all kind of additional information to either enforce certain connections or to prohibit certain connections. And it really depends on your goal, whether that is helpful for the outcome or not.
Yeah. Thank you. Any other question? I see no more cues in the chat, so I assume that that's it. Thanks again, Lisa, for your presentation. This actually concludes the BPI workshop. Thank you everyone for attending. I think it was a very nice workshop, very nice session, very fruitful. I see that the chat is full of comments and discussions that are still going on. So yeah, thanks again. Enjoy the rest of the conference and see you around somewhere in the week. Bye.
Thanks, bye.